Today's lesson is on matrix multiplication. First, we're going to talk about scalar multiplication. We can multiply a matrix by a constant number that we call a scalar. The product of a scalar k and a matrix X is xk, where k is multiplied to every element in the matrix X. So let's have an example. We have C equals this 2 by 3 matrix, and we're trying to find 3C. So we're going to take 3 times the matrix, and that's going to just take the 3 and multiply it to every single element inside the matrix. So 3 times 4 is 12, 3 times 9 is 27, 3 times negative 5 is negative 15, 3 times 2 is 6, 3 times negative 11 is negative 33, and 3 times 3 is 9. And that's how you do scalar multiplication. Next, we'll have an example where we're doing scalar multiplication and subtraction at the same time. So first I'm going to take the 4 and scalar multiply that to the 2 by 2 matrix. 4 times negative 3 is negative 12. 4 times 1 is 4. 4 times 6 is 24. And 4 times 2 is 8. Now on the second matrix, we can do one of two things. You can take the 3 and distribute the 3 all the way through, or we could take the negative 3 and distribute the negative 3 all the way through, and change the subtraction sign into an addition sign because you've distributed the negative all the way through. I think that might be the smartest choice, to distribute the negative 3 through. So I'm going to go ahead and do that. Negative 3 times 5 is negative 15. Negative 3 times 2 is negative 6. Negative 3 times negative 1 is positive 3. And negative 3 times 7 is negative 21. The reason I would like to distribute the negative through is so that I don't forget to subtract halfway through. That's the biggest mistake people will have with subtraction, is they'll subtract the first row and then all of a sudden the second row they forget what they're doing and then they start adding. So this way, if we distribute the negative through, we don't have to worry about forgetting. So I have negative 12 plus negative 15. Notice the two matrices are the same size, so they're going to produce another matrix the same size. So in the first row, first column, I'm getting negative 27. On the first row, second column, I'm going to add 4 and negative 6, and that gets me negative 2. Then I'm going to add 24 plus 3 to get 27 for the second row, first column. And then last, I take the 8 plus a negative 21, which gives me negative 13 for the second row, second column. And that's how you complete scalar multiplication. Now, matrix multiplication is much more involved than multiplying a scalar by a matrix. So we're going to return to our second-hand clothing store example to give us a summary of what matrix multiplication can look like and why it would be useful. So we have 3 store locations at Greenspoint, Victory, and Fairbanks, and we're selling pants and shirts. Let's disregard their color for this example. The inventory of the shirts and pants are described in the matrix I below for inventory. The price for each shirt is $8, and the price for each pair of pants is $15. So I can put the $8 in for the price for the pants in my price matrix, and $15 in for the pants for my price matrix. Find the value of each store's inventory. Okay, so right now, let's just use our logic and see if we can figure out how to find the Greenspoint store value. Well, I know the Greenspoint store has 64 shirts. I also know that each shirt is worth $8. So if I take 64 times 8, that is going to get me the value of all of the money I can earn from the shirts. Now the pants there's 98 pants at the Greenspoint store, and each pants are worth $15. Okay, so I pulled my calculator out. I've got 64 times 8, and that's going to get me the value of all of the shirts at the Greenspoint campus, which is 512. Then I need to add the value of the pants, which was 98 times 15. 1470. And when I add those two together, that gets me 1982. So I'm going to go ahead and summarize that data here in the matrix V for value, and that's going to get me 1982. Now let's do that again for the Victory store. So the Victory store has 66 shirts, and each of those shirts cost $8. Plus it has 132 pants, and each of those are worth $15 to the store. So if I take 66 times 8, that gets me 528, plus 132 times 15, that's going to get me 1980. And when I add those two together, I'm getting $2,508 of value in my inventory. And I'm going to go ahead and put that in the second row in my V matrix. And then I'm going to do this one more time for the Fairbanks store. And the Fairbanks store has 62 shirts times the $8. Plus we have the 49 pants times $15 each. 62 times 8 is 496. 49 times 15, that gets me 735. Then when I add those two together, that gets me 1,231. Okay, so I just used what I knew about value of a product, and I found the store's value with the shirts and pants for each of these stores. Now, this is the fundamentals of matrix multiplication. So my I matrix was the inventory, which is 64, 98, 66, 132, 62, and 49. And I'm going to multiply that to the P matrix, which was the price matrix, which is 815. And that got me the value matrix, which was 1982, 2508, and 1231. Now this can seem a little bit complicated at first, so we're going to go ahead and break it down a little bit further. I just wanted to see why matrix multiplication in its very intricate form is helpful. In this case, it is very helpful. I got my inventory, my price, and I was able to find the value. There's a few things I want to note about this matrix multiplication. First off, to get the Greens Point store value, we multiplied the first row of matrix I, the inventory, by the corresponding elements in the first column of matrix P, and then found the sum of the products. This is the basics of matrix multiplication. So I took the first row of matrix I and the first column of matrix P. I multiplied each of those corresponding values, and then I added their sum, and that's what got me the first row of my V resulting matrix. So that's just kind of some of the fundamentals of matrix multiplication. Another thing before we really get into the definition of matrix multiplication, I just wanted you to notice that when multiplying matrix I, notice matrix I was a size 3 by 2 matrix. By P, now P was a 2 by 1, 2 rows, 1 column matrix. We get matrix V. Now matrix V was a 3 by 1 matrix. Now this may seem a little bit random, but it's not. It turns out that the number of columns of I and the number of rows of P need to be the same. When you're matrix multiplying, the two inner size values need to be the same. And then it turns out that the resulting matrix size will be 3 by 1, the rows of the first matrix by the columns of the second matrix, which is how we got a 3 by 1 product matrix size.